Greetings, this is Shawn Chumbar, and this is my presentation for the short story assignment. This is my presentation regarding autonomous agents powered by large language models. You can find the survey paper linked in my GitHub repo. So to start off, introduction to LLM-based autonomous agents. So what are autonomous agents? They're systems that perceive, plan, and act within their environment, often with a specific purpose, such as completing a task or engaging in complex interactions. So the role of LLMs and autonomous agents are that they drive autonomous agents and they enable them to handle diverse, open domain tasks by drawing on knowledge and natural language understanding. LLMs help agents achieve complex human-like decision-making process that adapt based on context and interaction. So why does this matter? Because the integration of LLMs brings agents closer to AGI, which is artificial general intelligence capabilities. This allows agents to mimic human behaviors and makes them suitable for roles in fields like customer service, medical assistance, and task automation. So let's begin by talking about some of the core components of agent architecture. So this usually includes some sort of interconnected functionality where each component plays a role but works with other components, which allows agents to handle tasks in in human-like manner. The goal of the agent architecture is essentially a modular framework that allows LLM-based agents to function across various tasks. And the four key components of LLM-based autonomous agents are profiling, memory, planning, and action. Profiling establishes the agent's role and persona and helps tailor its responses to specific tasks or user needs. Memory stores past interactions and context and allows the agent to perform memory recall and build upon previous interactions. Planning allows the agent to break down complex tasks into smaller tasks and determine the best sequence of events to achieve its goals. And then action essentially executes the decisions and interacts with the environment and produces meaningful outcomes. So let's sort of talk about the profiling module first. So the purpose of the profiling is essentially assigning specific characteristics or identities to agents. It basically defines their role, the background, or the personality, and it helps it act as a certain persona, such as a software developer, technical assistant, or virtual teacher. The benefits of profiling is that it allows the agent to basically have consistent behavior, and essentially the responses will be aligned with the agent's role. So for profiling strategy number one, this is essentially handcrafted profiles, which are profiles that are created manually by designers, which specifies characteristics like background, personality traits, and task-specific skills. The strength in using this profiling strategy is that it allows for flexibility in creating highly customized profiles, and it allows for nuanced role-specific behaviors. Some limitations is that it is labor intensive to create a profile for each agent in a multi-agent system, and basically scalability is limited when performing large-scale implementations. So an example is an agent crafted as a financial advisor may have traits like analytical, cautious, and detail-oriented, which influences their responses to user questions about investments. For profiling strategy number two, LLM generated profiles. These are essentially profiles that have been generated by LLMs based on prompts or few shot examples. Some strengths of this is that it is efficient for creating many profiles, it is less manual work, but it does have limited control over fine details. So an example could be using prompts. An LLM can generate an agent profile with characteristics like empathetic and patient for a counseling bot. Strategy number three is dataset aligned profiles, and these are profiles that are based on real world demographic or behavioral datasets. It adds realism to agent behavior, but a limitation is that it's limited to the quality and type of available data. Agents can be aligned with demographic data, such as age, profession, or interests from a survey, which creates relatable personas for social research simulations. Next, we're going to move on to the next module, which is the memory module overview. And essentially, the purpose of memory is that it enables agents to store, retrieve, and use past information, which enhances continuity, consistency, and ability to learn from experience. Memory is important because it allows agents to build upon previous interactions and it creates more informed responses and adaptive behavior. So the different types of memory includes short-term, which is in-context memory, which is maintained within the prompt during a session, and it provides immediate context. The long-term persistent memory is stored in a vector DB or external storage and allows agents to retain info across sessions. So for short-term memory, basically it's stored within LLM's context window, and it's effective for handling tasks or interactions that rely on recent context without needing long-term retention. Some limitations is that it's constrained by the LLM's maximum context window length, and it cannot retain extensive or cross-session information. Long-term memory is a hybrid memory that combines short-term memory with persistent external storage and uses a vector DB for long-term information retention. The usage allows agents to store information across sessions and allows it to have historical knowledge as well. Some benefits of this includes that it enhances the agent's ability to adapt and perform effectively over time. Embedded memory is memory that's stored as vector representations, and it essentially allows fast and efficient retrieval based on relevance. It's common in complex high data environments where you need to basically filter and get information quickly. And embeddings allow for sophisticated, contextually relevant memory retrieval without direct access to full text memory storage. Uh, a memory operation that a lot of agents have is reading, and this is essentially retrieving relevant information from memory based on task requirements. And it optimizes agent actions by referencing past experiences. Some retrieval criteria to keep in mind is recency, relevance, and importance. How recent the memory was formed, how closely the memory aligns with the current task, as well as how important is the memory. Uh, a memory operation that's also included is writing, and essentially writing stores new information in memory, which helps agents retain useful data for future tasks and actions. Some challenges in this case is memory duplication as well as memory overflow. And another memory operation is reflection, which is essentially processing past actions and summarizing experiences to gain high level insights and inform future decisions. An example of this might be that an agent might summarize repeated interactions with the user as user prefers detailed responses, which guides future interactions. We're going to move on to the next big module, which is the planning module. And this module essentially allows agents to create steps in order to achieve complex tasks and basically break down tasks into smaller tasks. So basically, some types of planning include without feedback, which basically follows a predetermined path without adjustments based on new information. And then feedback planning also is a type of planning that is more dynamic and it's based on feedback and it leads to more adaptive and robust task execution. So planning without feedback is essentially single path reasoning. The agent basically generates one sequence of steps to reach a goal. And an example would be chain of thought reasoning, where an agent thinks through a problem step by step to reach a solution. Some limitations on this is that it's useful for straightforward tasks, but it will be ineffective in dynamic environments where the environment or the conditions change. Um, the other planning strategy is multi-path reasoning, which allows the agent to consider multiple solution pathways, and it essentially explores different strategies to achieve a desired outcome. So basically, it works by the agent would create a tree-like structure, which explores various steps in parallel or sequentially, and it rates each each uh, path's effectiveness. An example of this would be tree of thoughts, where each node represents an intermediate step or thought toward achieving a goal. Some advantages of this is that it's more flexible and it improves the agent's adaptability to complex tasks. It enhances decision making through broader exploration as well. Another planning strategy is using external planners, which is domain specific planning systems or algorithms that help agents handle complex tasks that require specialized knowledge. It works by converting the task into a formal representation, and this representation is processed by an external planner, which generates an action sequence. It's effective for apps that require technical precision, such as robotics, engineering tasks, or advanced simulations. And an example that they give is that LLM plus P converts text instructions into a structured format that an external planner can use to achieve accurate results. Planning with feedback, uh, environmental feedback. So, environmental feedback is essentially feedback from the environment, such as changes in the state or system updates. The agent basically receives feedback based on either the success or failure of its actions, and this allows it to adjust plans. For an example of this is the React framework, in which agents adapt actions based on outcomes of prior steps, and it incorporates a thought, act, observation triplets for iterative improvement. Some advantages of this is that it makes the agent more adaptable, and it also makes it more effective in unpredictable environments. Human feedback is where the agent will essentially uh, ask for guidance or correction from a human. And it basically works by the agent presenting its plan or action, it's reviewed by a human, and then that feedback that the human gives the agent is integrated into the agent's prompts, and it basically aligns with the user's values and preferences. An example of this is in the inner monologue framework. Agents request human feedback on scene descriptions and adjust based on user input. Some benefits of this is that it reduces hallucinations and it ensures actions are meaningful to the user. Model feedback is an internal feedback mechanism where the agent assesses its own actions and plans and allows self-correction. The agent basically generates an action plan, it receives feedback from an internal model or evaluation system, and then refines its approach. An example of this is that reflection uses a model-driven feedback loop to review and refine actions, and LLMs generate detailed feedback on agent decisions. A huge advantage of this is that the agent becomes self-sufficient and more resilient in task handling, and doesn't rely as much on external input. It allows the agent to be more self-sufficient. Next, we're going to move on to the next big module, which is the action module. And the action module essentially translates the agent's decision into actual outcomes. And this is the module where we're interacting with the environment and producing measurable effects. So how does it work? It's the final stage where decisions are executed and outcomes are produced based on the agent's memory, planning, and profiling. This module is basically the meat of the autonomous agent system. This is the module that is critical for ensuring that agent behaviors lead to real-world or simulated changes, and this enables effective interaction with both digital and physical environments. An action target task completion. Task completion is the agent's primary objective, which is to complete the task it's been given, whether this is answering the question, completing assignments, or solving specific user questions. The agent's actions are goal driven, and each step has to contribute to the successful accomplishment of a task. So, some examples of task completion include an agent that's a software dev. It might need to complete a function or suggest code fixes. In a customer service environment, an agent may resolve issues based on user queries. Another big key to this action module is communication. Communication is how agents engage in communication with other agents or humans, and it allows them to work together to collaborate on tasks or share information. It can occur through dialogues, sharing insights, or asking clarifying questions to enhance collaborative problem solving. An example of this is in chat dev. Agents exchange information to collectively complete software development tasks, improving task efficiency through teamwork. Another big portion of the action module is exploration. This is the agent's ability to discover new environments, contexts, or methods, and this increases the adaptability and learning of the agent. They basically engage in exploration to gather data or test hypotheses, and they balance this process with exploitation of known methods for optimal performance. An example of this is that Voyager enables agents to explore and experiment within the Minecraft game environment, and it enhances its skills through trial and error as it sees what works in the environment and what doesn't work in the environment. Some practical some practical applications across domains for AI agents include social science, in which autonomous agents can serve as virtual assistants or social simulators. An application in engineering is where agents can handle planning, automation, and simulation tasks in environments like robotics, design automation, and workflow optimization. And then applications in natural science, where in research and data analysis, agents can assist in hypothesis generation, data processing, and scientific exploration. And to conclude, some challenges in future research for AI agents. Some current challenges is scaling memory. So we have to manage large-scale memory across diverse tasks. We need to be able to ensure effective multi-step and adaptive planning. And we also need to minimize hallucinations and ensure our decisions align with human and ethical values. Some future research directions include enhanced memory management, in which we are developing efficient, scalable memory frameworks. Some advanced planning with feedback. We want to improve multipath and dynamic feedback handling, as well as human LLM alignment, in which we're going to implement techniques to reduce errors and biases in agent responses. Some conclusion and key takeaways for this presentation is that autonomous agents powered by LLMs are transforming task automation with human-like intelligence. The four core modules are profiling, memory, planning, and action, and these make agents more versatile and goal-oriented. By advancing memory handling, planning, feedback, and aligning with human values, autonomous agents can become more reliable and effective. And some final thoughts for the reader or for the viewer is that the future of autonomous agents promises greater integration across industries with evolving capabilities that bring us closer to achieving AGI-like applications in real-world settings. I am Shawn Chumbar. Thank you so much. That was my presentation, and have a good one. Thank you.